Hi everyone, this is the talk I gave recently in the Armstrong State University titled The Riemann Sums and Fundamental Theorem of Calculus. This is really a question and I raised it, myself raised too about the Riemann sums and I thought about it, doodling a little bit here and there and looking up and found an answer, and I thought it is something everybody knows. Whoever learns calculus know about the Riemann sum, and it's a fine question and an answer to that Riemann sum. To talk about the Riemann sum, I'd like to talk about this limits and asymptotics first. This arrow symbol in here is for limits, and this wavy symbol here is for asymptotic. Limits are defined as follow. At minus bt, if that approaches 0, we write it like this. At is approaching bt. We say as At is asymptotically equal to bt if At divided by bt approaches 1. Sometimes this one is an accurate measure of the behavior of this function. Sometimes this is a better accurate measure. So for example, as t approaches 0, if At is 1 over t plus 2 plus 3t, if bt is 1 over t plus 2, we're going to consider the limit, and it's whether At approaches bt. So we have to take the difference. As you can see, if you take the difference, you're only left with the 3t here. That 3t obviously approaches 0 as t approaches 0. But if you look at this term, and 1 over t is becoming larger and larger number. We don't usually in calculus consider limits when these are approaching infinity, but we're actually using that idea to compare this fast-growing function as t approaches 0. We're still saying that since the difference is approaching 0, we say that At is approaching 1 over t plus 2. Although there's one more term in there that's negligibly small. And in particular, we don't say that At is approaching 1 over t. Seems like t really doesn't matter. It's mainly this term here is really big, but we still don't say At is approaching 1 over t. If you subtract these two, 2 is left out. So it's very sensitive about the little terms as well. The next one will be asymptotic. So we're looking at the same two expressions. To think about the asymptotic, the thing to consider is At divided by bt. Now when you consider the quotient of these two things, better not have this t in the denominator, is easier to see, so I multiply these t's both sides. As you can see, that after you multiply this t, you get this polynomial, 2t and 3t squared. If you multiply t here, then you get 1 plus 2t. So as t approaches 0, then this whole 3 terms approaching 0, leaving it as 1. So this At divided by bt is quotient is becoming almost the same. And we say At is asymptotically equal to this target 1 over t plus 2. Interesting thing is that before At does not approach 1 over t, but this time approximation, this asymptotic expression, actually ignores this type of a big behavior. In the quotient, this kind of disappears. I think that's my next slide in here. Before At is not approaching 1 over t. Now this time At is asymptotically equal to 1 over t plus 2, but also At is asymptotically 1 over t. So if we don't have this full information, we don't really know At is really close to that or close to that. Asymptotically, they're all kind of equivalent. So asymptotic behavior is mainly about this. If At that we are looking at is a large quantity, then we just focus on this, the main term, that big chunk that contributes to the sides. Again, that's convenient. It is good enough and sufficient enough sometimes, but again, if it is really the case, if there's some significant term like 2 is there, this asymptotic formula does not distinguish whether there's a 2 or not if you have just that information. Here's another example where n is approaching infinity. So an is given by this formula, and suppose we don't know how this formula looks like. We only have a data or some experiment, a recursive formula that is all we have, and realize that, oh, if you divide an divided by n is roughly 1, it is kind of have a tendency to 1, that you can conclude an is asymptotic to n. But you can also ask that question, is an really approaching n? That means if you subtract n from it, is that going to approach 0? So there's some phenomenon going on, and if this is not available, if it's too hard, then definitely we just focus on, okay, what is the main size in here? So those are the two things, asymptotic. So suppose we have that fact an is asymptotically n, and the fact is that it's actually an is approaching n minus 2, not n. And this can be obtained by doing the long division in here and easily figure out, and that's the polynomial term, and there's rational part that approaches 0. So these are the actually two facts, and I'm going to go into the next level. So if you subtract, and this is one idea to how to kind of improve this asymptotic formula. If you subtract 1 n from an, then it's negative 2, and it's approaching that. If you think about it, this is also good enough to conclude asymptotically equal. So we approach also this an minus n is asymptotic equal to negative 2. So to go from here to there, it seems like our goal throughout the talk. If you discover one asymptotic formula, how do we improve that? If you just keep looking at this asymptotic formula, you can't distinguish n from n minus 2 or n plus 2. So you subtract off that main term and see how that behaves. It's a lot smaller because we took off a lot, the big chunk of it. And then you do investigate asymptotic question again, then the answer will be that asymptotic formula is actually constant, and you're going to discover something like that. So that's how we're going to go. And you can do one more. Okay, I took out this 2 over there, and then what is left out. At this point, by knowing that an approaching n minus 2, that an minus this whole thing is going to be 0. So this is where a subtle thing happens. Before, this limit idea is more precise, more accurate, and as soon as you enter this level, and we know this is something approaching 0, so the limit does not distinguish anything. If I can just put arbitrary thing in here, like 1 over n squared plus 5, something like that, that still approaches that because that's a 0. But if you look at asymptotic, that becomes sensitive. If there are quantities that are very, very small, close to 0, the ratio, as you probably noticed, is called indeterminate form. We don't know what's going to happen with that simple information. They're both approaching 0. So this turns out at this level, going deeper to the small level, asymptotic becomes meaningful and limit has no meaning at this stage. I just had this fun with this particular example, just to introduce the idea of asymptotic. Pi is the transcendental number, and this is the decimal expansion of that pi, and 3.14 those number. And I consider certain function, an, which is the sum of all the decimal digits up to nth digit. So how it's going to grow? One idea is that these all the numbers are integers between 0 and 9, so they're all less than 9. Therefore, this never exceed 9 times n. So we got some idea, an doesn't grow that much. So, but what is it? Is it asymptotically root n or log n? What kind of function is an's growing as you add up all those integers? Very curious. It turns out, and people consider this type of thing, is called normal number. It's actually saying doesn't matter what the basis you consider, that is going to always turn out to right in the average of 0 through 9. So average of 0 through 9 is 4.5. So they're expecting that the sum of this all the digits up to n digits is roughly asymptotically 4.5 the average time of number of digits you added. So this is well believed, and are there proofs? And it seems like there are 2 proofs out there, and experts are saying it's very difficult to understand. So it doesn't seem like people really understood or believe that actually true. But it is a published proofs. So our idea is, okay, let's believe that 4.5n is true. What's going to happen if I subtract off that big chunk? What's going to happen to the remaining part? And I didn't find any result on that part. So, but I stated here, so what is the next level of asymptotic formula? I had no idea. So I looked at the graph. I used the computer software to sketch the graph of Sn minus 4.5n. So I went up to the 5,000 digits, and it knocked down a big chunk of number. Still, it grows up to 300, 210, 100, things like that. And as far as I know, it keeps oscillating like this. Pi is highly associated with its trigonometric functions, and maybe there is something why I'm just speak unintelligently right now. I don't know what's going on. It's just simply the data. I played with the root n, third root of n, and that really seriously knocked down this function. Well, my purpose in here is introducing the idea of asymptotic formula and how to go deeper and deeper. That was some formula that problem that I had fun with. But there are other well-known asymptotic formulas out there in number theory and combinatorics, counting things and calculating things that we never expect that there's an exact formula. So there are some classical examples. So let me introduce that. Prime number theorem, probably most well-known asymptotic formula among all the others. Pi n is a standard notation. Pi is not the transcendental number. The pi n is a standard notation for the number of primes up to n. Okay? Then the result is that asymptotic formula of a pi n, number of primes up to n, is n divided by ln. Again, there may be a big chunk of his weighting in here is hidden. We don't know, if it's really correct or not. This information is leaving out huge chunk, but that chunk is relatively smaller than that one. But it still could be a large number, but it's far smaller than this chunk in here. Well, this information is often good enough about following type of information. Suppose this is number of primes. Suppose you divide everything on both sides by n, which behaves nicely because it's multiplicative definition. So pi n divided by n, right? Pi n divided by n. Let me write that down. I have this wonderful tool called Epic Pen in here. So pi n divided by n is too thick. I'm going to make it too thick. So that's gone. So that is 1 here, right? So what does that measure? Pi n divided by n. Maybe you know what it means, but I'm going to show you the next picture to show you is more meaningful. I like this idea on here. Suppose there's a 1,000 balls in here, all numbered from 1 through 1,000. And you randomly just mix it and get one number out of it. And what is the chance that ball is the prime number? So it is, disregarding how these numbers are distributed on a number line is all about random, mixture of a number. And that's exactly what this one is measuring in here. Let me use that divided by n and with 1 in there. So that's the total number of balls and total number of prime numbers, and what's the probability is measuring 1 divided by ln n, right? So I use 1,000. What is ln 1,000? This is log e, and it was roughly 14%. That's what I remember. Where do you write that percent symbol here? Yeah, 14%. But if it increases to 1,000,000 balls, then you can see this getting smaller and smaller. That's the situation right there. Alright, that could be the meaning of this one. Although we don't know anything else is going on, below this level, that is good enough information about the probability kind of thing. So that's well known formula. What we were doing is that, okay, let's subtract off the main term. And what is the next level of this thing? And this prime number theorem is built around this nice complex theory and Riemann zeta function and Riemann hypothesis and all that allows us to go deeper to the level, and this is well known. So it turns out it is n divided by ln squared, and the next level after you subtract it off is ln cubed, and with a 2 factorial, or I think there's a 2 factorial, I think I missed that. Sorry about this typo. I think there's a 2 factorial in here, and next one going there, things like that. Alright, apologize about the typo. But these are the very well-known asymptotic formula. And also, the distributive square of free integers for number theorists is also interesting thing, up to n. Each number, it has unique factorization into prime numbers. And what are those the the number of numbers, that unique factorization, prime factorization does not involve any multiple factors. All one prime factor multiplied by another distinct prime factor. So it turns out the 6 over pi squared is a familiar number, right? The sum of pi squared over 6 is the sum of the squares of the reciprocals and things like that. So again, this is built around the Riemann zeta function, and that's where the zeta value of 2 kicking in. But this does not seem like the next level is completely known. There are lots of work on inequality on that one, and with the Riemann hypothesis you can sharpen that, but I'm not sure I've encountered the exact formula for here that we can call this asymptotic. But so as you go deeper, the problem gets harder. And this is area from combinatorics. It's very famous and highly non-trivial technical work. Is the number of partition of n. So way of writing n into a sum of different number, not counting the order of that, and that's the partial asymptotic formula. This is proved by Hardy and Ramanujan, and this is not the picture of them actually. This is both actors in the movie. It's coming up probably sooner or later. It's the movie The Man Who Knew Infinity. But I had fun with this photo in the talk. So, but that's done by Hardy and Ramanujan. Those are very fancy and historically significant problems and answers. But here's something that we encounter all the time in our calculus course: is this tangent text and this Taylor series of tangent texts. One way to approach this AK is keep differentiating the tangent text, and you might know that it gets, because it's a quotient form, it gets highly complicated. Another one is using the arithmetic. So here's the arithmetic version. If you have a sine x divided by cosine x, we know the Taylor series of sine x and Taylor series of cosine x very well, and then you can just kind of fill in, and it's followed in the following form: cosine x over there. You want to fill out, this is supposed to be tangent x, and I want to figure out a1. Because we know it's an odd function, you can skip one of the parts and then go, okay, a1x, and skip the even term and go to a3x, like that. And if you multiply out and compare the coefficient with the sine x, one thing at a time, inductively, you can figure out a1 and a3. You do not need any derivative or anything. It's very arithmetic structure in there. From there, we can get our hands on that. But our question is that is there some exact formula to that? At this point, no. But next question would be, if you don't quite understand what is the next question, and the whole theme is that, what is the asymptotic formula? How is this AK grows? And when you consider Taylor series like this, and we know the radius of convergence is very important, you can't just write out those calculation and claim it there. You have to claim that, oh, this is actually radius of convergence is positive, therefore it's a meaningful Taylor sequence. So this asymptotic formula is sufficient enough to conclude what the radius of convergence is. So there is our simple question in our calculus course, and it will be answered in this talk. But that's one natural asymptotic formula that kicks in every day of our business, teaching and learning in mathematics. Okay, now let us introduce our asymptotic problems. And I like this formulation better than the other one that will be shortly introduced. But when we focus on detail part, that formulation is better. But this seems like a more fun problem to consider for asymptotic sense. We usually consider asymptotic for some function that grows. That's why. So suppose we have continuous function defined in 0 and 1 on a closed interval. And this xk is evenly distributed n points in between 0 and 1. Okay? And our Sn is the sum of all that function number, f of x1, all the way to f of xn. So if you choose 1,000 points in between 0 and 1, then it will be sum of 1,000 values. Like the digits of a pi, we have some sort of idea of what's happening to f of x. This continuous function, by extreme value theorem, there's always a maximum value on top of it. So that each of the function is always less than equal to m, where you're adding all these m's those m are, sorry about that, my maximum number and maximum value of this function. So there are n of them, so n times capital M. Fair enough. So we know it is again the linear behavior according to this E, this linear behavior, n times M. Sorry about that. I was distracted with a message that popped up. Alright, so, but what is that really the value? So I think I'm introducing this example. So here is my favorite function, 1 over x squared plus 1. Then I chose many values in here and add them all up. And after you plug it in there, add them all up. That's the Sn. So I'm showing the graph of Sn done by computer software. So this means if I throw in 50 points in between 0 and 1 and add all the fractions, 1 over x squared, and the sum turns out to be just a little bit low, like 48, or I probably 40 or around that point. If you go up to 200, that number is close to 150. Alright? That's the meaning of this graph. You throw in 200 points in between 0 and 1, and you get the sum roughly 150. But what you notice that is that we're looking for a formula for Sn, and it looks like a straight line. So that's our first contender for Sn. Alright, here it is. So it seems like Sn is asymptotically equal to Cn. So I have the data, so why not? I calculated that number all the way at the end, 200. Turns out it's at 0.784147127173. That's the number. Alright? But if you remember about the picture, it's not only just asymptotic, it seems like it's the straight line itself. So why don't we ask this question, that is Sn actually approaching its limit? And I did that, and I subtracted it off and see if it is a 0. When I subtract Sn as Cn minus from Sn, I got another line. So that made no sense to me. I took off a line, it should be something else, something that's, behave different than a line. So I figured that this number is probably not accurate. So I really bumped up the data a lot, so improve that value and subtract off and see if I have a next picture there. So I have to go sketching the Sn minus Cn. What happened to the remaining part? Alright, turns out it's like that, and this is depending around is around the point negative 0.2501, and the data value Sn minus what was the value, C times n, is becoming like that, so around the 1000 value. So here is 0. I think this part is not 0. The 0.2501 and this 0.25 and 0.2501 and so on, I think. So it's very small, 1/10,000th units described in here. So it seems like it's approaching that 0.25. You can't just conclude things like that by looking at the picture. Maybe that is approaching C1, or loosely said that it's asymptotically C1. Maybe it's behaving like ln. If you look at far to the right of ln, it looks just like a flat line. So how do you know if it's behaving like that? It's really approaching. So, but we have some contenders here. Very slow growth, or doesn't grow at all like this. That's our problem. We just looked at one approximation, and let me just use this example to describe our problems and the future problems. That if you subtract off Cn, what is this asymptotic formula there? Once you figure that out, you subtract it again to decide what is the next asymptotic formula. If I keep doing that, s times, then you're asking the question, okay, we subtract of all these nice asymptotic formulas off that, and what is remaining and how this one grows, and that is our problem. We want to find systematic way of computing these asymptotic formula, and one layer after another. And right now it seems like the very first one is linear, C times n, and then approximate value seems like 0.7841 and so on. So that's our problem right there. We have a function in general, continuous function, add all this bunch of numbers in between 0 and 1. Where are they going? And what is the asymptotic formula of a deeper and deeper layer? Now let me introduce the real formulation. The answer to the first layer is really the fundamental theorem of calculus. That Sn is in fact asymptotically c times n, that c is really the difference of the values of these two antiderivatives. So let me clarify the meaning of all this thing in the calculus. This one is called definite integral, and it is not defined as this difference of antiderivative. It's actually defined as like this: the sum of all the numbers that we defined in here considering divided by n. So that's exactly the definition of this notation. This connection of these two is called fundamental theorem of calculus. But also the existence of this number, when you formulate like this, before we calculate any number, maybe it's all changes when we enter n to some number that we cannot even imagine. So knowing that there is actually c exists, and such that this asymptotic formula happens, is important, the existence. Which existence is namely existence of this definite integral. Why is this definite integral exist? And then this is also asymptotic form, it is equivalent form. So for this right regular Riemann sum, the existence of integral is first established by Cauchy. For general Riemann sum, this contribution is not from Cauchy, but Riemann himself actually did not write that down. But anyway, here's an existence this is part, and fundamental theorem of calculus allows us how to calculate this number c. It exists by continuity, and what is a c? That's a fundamental theorem of calculus. So we have that definite integral equal to that. It's not definition again, it's a theorem. So we're going to formulate this, our problem, as a regular right Riemann sum problem. There is our sum of all the values. If you divide it by the n, that's our regular right Riemann sum. So here Sn divided by n. So our original asymptotic problem is Sn minus our content A0, which is the definite integral value, and next one found it subtracted off, and things like that. That's our original problem. But if you divide everything by n, we're going to enter our asymptotic target for Riemann sum. Here's a regular right Riemann sum. And how does that behave? First number is a constant, that is the integral value, as you divide everything by n. Then what is the next one? And what is the next one? This is simply divide all the formulas you have by n, and you arrive at here. But we're more familiar with this Riemann sum. I'll switch to that problem for now. Whenever we have some result, I'll remind you of the version for Sn. So that our asymptotic problem is reformulated. Right, I realize that I wrote down neatly here again. So that's our problem. Riemann sum, what is the asymptotic? We'll look at this couple more times about these examples, but right now we know more about that c. We know that c is integral of that. So if you calculate that, this is a well-known antiderivative, arc10, so you arrive at pi over 4. The actual pi over 4, several digits, 0.7853. 981633 and things like that. Even you go up to 1000, you don't even get to this type of number that the way I calculated before, and being at 1000. So it takes long to get this precision. So here I'm showing clearly again our asymptotic formula in this way. I think it depends on what's on the next one, so let me take a peek. Oh, that's right now. So this notation is a little bit annoying, maybe negative and all that. So they'd like to introduce a new notation. So to write this phenomenon again, so that is called little o notation. So I wrote down that property again. If you subtract of this very good analysis and what is still asymptotic too, if it's not exact, and we're going to write it like this. Rn is actually have this portion, all the asymptotic layers we discovered in here, plus whatever is left. We're going to call that one little o of gs plus 1. So we're not specifying what this one is, and we just use this little o notation to indicate the property of this remaining part. So here the ln actually represents the remaining part, and we're saying that ln has the property of being little o of gs plus 1n. What that means, if you take that remaining part and divide it by gs plus 1n, it's not 1, it's approaching 0. So it's compared to the size of this one, this is far smaller. That's what it means. So whenever we accomplish this level correctly, rest of the part is far smaller, then we'll just write it like this. And equal symbol and all that, it's more comfortable and more familiar. That it seems like we're actually looking at Rn and not something else. So that's the notation we're going to be using to indicate this much of a work done. So here again, once again, the formulation of an asymptotic formula that we're looking for regular right Riemann sums. Alright, I think all calculus classes with this simple example, monomial, and consider the Riemann sum. So the simple one is, general formulation, x to the m. So instead of x, now we plug in k over n, that's xk. And, well, n has no k in it, so we can n to the m can go outside in here. So that's why we have 1 over m, n to the m plus 1. And the rest of the pod is the sum of mth power up to n to the m. And when m equals 1, m equals 2 is usually considered in most calculus classes. But in general, we want to know what the formula is for sum of all the powers. Let me rewrite it here so that you remember what this one is. If m is, for example, if m is 3, we're looking at the sum being 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed when m equals 3. That's the formula we're looking for. And I think that was n plus 1 and divided by 2. That's the sum of first power, but it was squared or something. But what if m is 4? What if m is 5? Is there a systematic way to do that? Probably somebody must have done that. It seems like a natural problem. So historically, it seems like Johann Faulhaber is the first person who wrote down the formula up to that m being 17. But of course there is some beautiful description of that formula, and he had not known back then, but we will see that, and it'll be introduced. Let's move on. And at that point, and I remember I was actually thinking about this problem on my own, and then just didn't care much about this one, but continued to just examples and to formulate kind of the shape of the function, the asymptotic formula that I was looking for. So I start with x in there, so the k to the first, right, and 1 more power, n squared. So everybody knows that formula, sum of 1 through n is 1/2 times n squared plus n. Okay, so if you divide by n squared, then you arrive at your 1/2 plus 1 over 2n. We just focus on that one. That's the actual integral as this one approaches 0. But we are now paying attention to this part as well. That's the whole deal about this talk. And let me remind you about Sn. Sn is Rn multiplied by n. Right? That's how you get it here. That is the sum of the value. It is the average of that value. Okay? So Sn multiplied by that. We have 1/2 n plus this constant 1/2. Alright, that's the sum. It's not asymptotic or limit, it's the exact formula. It's a simple function there. Next one is x squared. Many of us also know this formula, and we usually introduce it as a product form like n plus 1, 2n plus 1, things like that. But if you expand that, and you get this formula there. The point is that these are cubic form polynomial, and there is a cubic, and cancel. We picked up 1/3, and integral of this one between 0 and 1, 1/3 picks up there. Now we have slightly more terms, and there's an exact formula. Curious, there's a 1/2 again, so I'm going to the third power, and I already showed you the formula third power. So we have fewer terms but higher degree, and then to the fourth, again third power and the fourth. Cancel, it gives a 1/4, which is the integral of this one from 0 to 1. And then we have 2 more terms with a higher level. I hope I got this one right before. Let me go back, n squared, yeah, it happened that way. Now I'm showing the n to the fourth. I didn't know about this one, I had to look it up. But anyway, this one unfolds like this. 1/5, there's again the 1/2 still, and this number begin to change and all that. Alright, so okay, of course it goes in patterns clear, then there's a 1 higher degree and all that, so I knew it looks like this. And if you enter whatever the polynomial, the more polynomials you calculate from Faulhaber problem, then it's going to be in that shape. And our Sn is going to be in this shape. If you multiply by n, that a0 is integral of that, so 1 over n plus 1. And the second one from our observation, it seems like it's always 1/2. And that is something we have to explain. But rest of the part begin to have 1 over n in there. 1 over n, you know, and whatever the stuff in a 1 over n squared and things like that. You know that whole thing, because it's truncated, it's not infinite series right there. So as n approaches infinity, that definitely approaches 0. So this O1 is a nice notation for something that approaches 0, right? Because, okay, whatever that one is, ln, if it divided by 1, that approaches 0. Remember that definition of ON? So that whole thing is approaching 0. Okay? So it seems like this observation. We'll get a better explanation about that 1/2 later. But this is my observation. Let's try to look at the big picture. I started with the function f of x, and then I consider that there was this polynomial. I don't know exactly how this coefficient looked like, but there was this polynomial such that if you plug in 1 over n in there, then it becomes a Riemann sum exact way. Of course, we don't expect this type of exact formula for the general case, but it gives us an idea on how to formulate this asymptotic target. So here's a big picture. I started with a sum function x to the m. I got this polynomial out of it. I'll stick in 1 over n, and that's the Riemann sum. So again, we don't expect the polynomials here in general case. And what could be the best scenario? I guess it is a power series. So f of x, you started with that. And we're expecting there's some sort of power series associated with this f of x, such that if you stick in 1 over n in here, and it becomes a power series exact formula. Once you have this exact formula as a power series, you can just truncate it in here, look at it as an asymptotic formula. So I'm actually expecting a lot more than asymptotic formula. I was expecting f of x is there, and I'd like to come up with this power series where you plug in 1 over n, it becomes a Riemann sum. For that, we can interpret it as asymptotic formula. Before I talk more about this power series, let me clarify the difference between these deeper asymptotic formulas and a series of a function. So usually the series of a functions are denoted like this. So the key point is that where t is fixed and while s is growing, what happened to this infinite series? That is the main target of our series of a function. But our asymptotic formula is a slightly different point of view. S is fixed in here. You cut the level and see what happened as t approaches 0. So as S is fixed, as t approaches 0, I get certain number in here. We're going to make sure is remaining part of our Riemann sum is far smaller than our smallest target we have playing with it in here. So again, for a series of a function, t is fixed and s is approaching infinity. Very difficult to sometimes determine whether even if it converges or not. And here, s is fixed. It's just about one part of the behavior. So usually there's no issue of convergence at all. So this is the stock difference in here. So for that Taylor series problem, my next easiest contender was e to the x. So I have this Riemann sum in here. I was looking for some sort of Taylor series formula such that Riemann sum is the Taylor series of 1 over n. So I enter the Riemann sum. There's a k over n. And something really nice thing happened. If you isolate it like this, that doesn't have k in it. So this is a geometric series. All right? It's a very good exercise for those who are learning the geometric series. And then here's the geometric series, and here's common ratio is r. So let me show you that formula in here. So the first term, a, what is the first term? If we use this 1 there, if you plug in a 1, that's e to the 1 over n. Then we multiply by common ratio 1r, 1 minus r, and up there 1 minus r to the number of terms you're adding in here. If you look at this index, number of terms we're adding is n, so therefore n goes in there. So that's what you're looking at in here. R is e to the 1 over n. That's what is in there. Okay, then this 1 over n cancel. It becomes 1 minus e, and out there. E to the 1 over n is up there. So nicely organized. It's very nice. 1 over n here, 1 over n there, 1 over n there, right? So we can write this one as a function of t. I didn't expect that it's going to be neat like this. I was expecting some power series, but it turns out, just like the Feldhaber's problem, there is this nice closed formula for the Riemann sum. That's very, very nice. But we want to use that. Here's a big picture again. F of x is e to the x. That's the function we started with. And Riemann sum is expressed as like this function in here. So my question was that I start with the f. What is this function g? What is this connection? All right, here's our asymptotic formula problem formulated again, and this function in here. Well, my original problem is that, I don't expect this neat formula shows up in general case, so I'm going for the power series right there. Start with a function. What is this power series whose Riemann sum is exactly equal to? I mean, this is supposed to be infinity. So about this typo, this is supposed to be infinity in here for equal symbol there. Again, 1 over n is fixed, and then we're approaching. This is a lot more than an asymptotic formula. But once you have it again, you can truncate it in s, and then look at it as an asymptotic formula. All right, let me go back and emphasize it. This function and this function in here, I recognize, I know that function. And I hope you really recognize this function as well. T divided by e to the t minus 1. This one is introduced in probably virtually all combinatorics class, if they reach down there to some generating function part. It is the Bernoulli's number, and here's the Bernoulli's picture. So what is Bernoulli's number? Bernoulli's is called the first Bernoulli number. Notice that there's a tilde over there. That's just a Taylor series of this t over e to the t minus 1. So that's the definition. So we don't have an exact formula for that. It's just called BK, but there is an asymptotic formula for the BK, of course. So here's some Bernoulli number. Notice that I lost that tilde symbol in here. Difference between BK and BK tilde is only the second term. BK tilde is a negative 1/2 and BK is a positive 1/2. And this one is called second Bernoulli number. Alright? This one is called B0 and B1 and so on. Let me show you the first two terms. So it looks like it's going down, but showing you that a B20 pick up the sides and eventually gets a lot bigger than these first few numbers. Remember, the function we had is not t over e to the t minus 1. There's e to the t times the t. And here's a really neat trick that connects to the first Bernoulli number and second Bernoulli number. I divide both sides by e to the t and e to the t. I mean the numerator and denominator. Then we enter e to the negative t. That cancels, and it cancels like that. Swap it around and put in the negative. We enter the form of u divided by e to the u minus 1 again. So that's exactly what we had before, with a negative in there. So what's the difference between these two? So I'm going to plug in -2 to the first kind of Bernoulli number, I think, and compare that first Bernoulli number and second Bernoulli number. So here is our formula, described as original Bernoulli function. Plug in -t to the Taylor series, and then you pick up the negative symbol in there. So putting these two together is called the second Bernoulli number. But this still does not explain why the only second term is different and everything else is the same. Is that if you just use that first two terms, it gives you a linear function in t. If you subtract off there, I think that is e to the t t minus 1 minus, I think it was 1, that was minus 1/2 is original first kind of Bernoulli number, right? That's the first Bernoulli number. If you subtract of that, rest of the part starts with k from square to infinity. That's the first kind of Bernoulli number, like that. T to the k, like that. And it turns out it's not easy to see why this is an even function. But you can apply negative t, and you will see in the numerator there's a symmetry happens. And if you combine it to the same time, the symmetry happened, and you can see this is an even function. Some surprising property that you don't see it here, but as you simplify, you will see this is an even function. Therefore, it loses all the even power in there. It's only odd power that survives. Or I said the other way around. Let me go ahead and clarify that. I should have known better about the Bernoulli number. As you can see, 0, 1, 2, 3. So we lose even function is correct, and this we're losing all the odd powers in there. 2n, of course. I knew that. I just got tired of all this thing because I'm doing the second time. But let's continue in here. Oh, it's wrong slide. So when you switch to that, although it seems like it's picking up all the negative, all the odd powers are 0, and even powers, except the very first one, they're all the same. So not much of the difference between bk and bk tilde. So I'm reformulating our problem, asymptotic problem. So our function, and there happened to be this wonderful function in here, such that if you plug in 1 over n, that becomes a Riemann sum. And also we got this Taylor formulation of that Riemann sum in here. Again, this is a lot more than as asymptotic. So I'm summarizing switch of my focus at that point was I was originally just looking for Taylor asymptotic formula. I realized that if you have Taylor series, the asymptotic formula is just, you just truncate it, and that becomes asymptotic formula. So I was going for Taylor series. And here's actual few terms that I list them out for e to the x to compare some of the calculation we had done before. So e minus 1, that's the antiderivative, not antiderivative, definite integral of e to the x from 0 to 1. And there's 1/2 again, but this time multiplied by e minus 1. Okay? And then there is this Bernoulli number kicking in. That involves Bernoulli number, right? That's one asymptotic formula coming from the Taylor series of Rn, which we discovered. So here's a sine x, and the formula gets complicated, and people just, all those formulas, and we can do it with the formula. But I also introduced an interesting idea, which I use when I introduce sums and series in my Calculus 2 course. So rather than starting with the CK, it's all about the sum formula, and try to figure out the sum. The other way around is a lot easier. It's just like differentiation is a lot easier than integrating the same phenomena. I started with this simple formula and figure out what could be the inside the sum end that gives this formula. So if we expect this one has nice, recognizable function, and then you just try all the recognizable function and see what kind of integrand, the sum end we have here. So I started with a sine n. Realize that throwing in some constant doesn't do anything, and it's a more general version, so that's why we're doing it here. So how do we access this CK? Just subtract the adjacent term. That makes sense. This is sum up to n, all the way up to n. Up to n minus 1, so subtract the last term Cn. Alright? The key thing is that this is only valid for one higher indices. The very first one doesn't fall into this idea, and that's often it becomes very significant term, n equals 1 in here. Now how are we going to simplify this one rather than leaving it like that? It looks like a telescoping sum, but there's an addition and subtraction formula. If you combine that, this one becomes sum of these two angles divided by 2, and that one in here, difference of angle divided by 2. So this one actually got simpler. Rn cancel, and this becomes some constant, relative constant. Let me show you that here in the next level. So Rn cancel, r over 2. Rn divided by 2, alpha n, sorry about that, and minus negative alpha over 2. So this is a constant when you stick this one in here and claim that, oh, I discovered this wonderful formula. But there's this weird term out there. But it's still interesting formula. You can isolate that and claim you found a formula for some of the signs. So it is not very difficult to consider other versions of trigonometric limit. Is there, considers another linear function to get rid of this alpha over 2 such that you have a clean alpha in there. So I'll skip that part. I'll give you the, you might bump into this one. It's not too hard. So if you consider this one, you can also do sine, but many formula uses cosine version. So I use this cosine. And if you throw in alpha over 2, and if you do addition and subtraction formula business again, now alpha over 2, got rid of it, and disappeared, alpha k, and here's alpha over 2 there. If you stick that in there, then we have one nice formula of a sum of sine of alpha k right there, and all the other things is a constant multiple, and then we can pull out and move it over to the other side. Also, there's n equals 1. Whatever you get out of that, that has to be cleared as well. So, although the following formula looks complicated, and this is a fairly straightforward algebra, it's fun to do on your own. And we're going to apply that alpha with a 1 over n so that it looks like a Riemann sum in there. So once you do that, alpha being Riemann 1 over n, and move one term over there and divide everything by the sine of alpha over 2 and all that, you arrive at this horrible formula. But it is a closed formula. Right? It's a great. Excellent. So again, you go and expand it into Taylor series and then get some idea about how this asymptotic formula looks like. But I got a lot more than even Taylor series. I got a closed formula. Alright, so I thought it's fun to share that Sn version than an Rn version here. So Sn, if you use this version, Sn becomes 1 minus cosine 1. That's the integral value of sine x between 0 and 1, multiplied to n. Then here is this constant term that is curious, 1/2 from the Bernoulli number, and here's a sine 1. Now it reveals, it seems like it's just that function value there. So it begins to reveal the one level below of our sum formula. Right, now it's formulated the Taylor series problem we're looking for. So this time even we started with a Taylor series of given function, and we consider the Riemann sum as a Taylor series of 1 over n. So we're looking for gt such that if you stick in 1 over n in there, and it is exactly the Riemann sum in here. So start from Taylor series and end up in Taylor series. That's our goal. So from here is our solution. Becomes a lot more technical, and I'm glad that I got this chalk cursor back, I think. So let's start with this thing without a 1 over n. And is k to the n, this Riemann sum part, and this is the Taylor series of f of x. So Taylor coefficient. X to the m is replaced by k over n, which truncated version, we already did that in Faulhaber problem. Next, and I'm swapping the sum of these two things. It's a power series, and you can do that. It has absolute convergence and all that. So b to the m, and bm here has no k in it, so you can pull it out. N to the m, like before, has nothing in there. So only this is, again, we pull out this Faulhaber problem. That's the coming from the Riemann sum index, k through n, and here that. So we don't know the general formula at this point, so I'll just replace that with notation. We know that that we can explain this one is actually the polynomial of degree n to the m plus 1, and whatever the coefficient, this is how they historically labeled. There's m, the whole thing that is fixed across the sum, and then these indices in the second slot in there. So basically this one is polynomial of n to the m plus 1, losing the without a constant term. So this n squared. So we write it out like this, and then we'll look at this coefficient later. So I'm going to replace that with a polynomial of degree degree m in n. So that is copied in here, and that part is replaced now. It's polynomial part. So n came down. This is mainly n to the something with something multiplied in here, and the degree is going up to all the way up to m plus 1. So the case starting with a 0 makes sense, and n to the first is the lowest term, so therefore m is fitting in there. So we got this one, and switch to m. Then realize that n to the m and n to the m cancel, but we still have n to the first left, so I pulled it out. Bm is still out there, and then we have n to the k in the denominator and this coefficient. Alright, so that's currently the shape, and the CMK came from the Faulhaber polynomial or coefficients. So what we're going to do, I think, next is that I don't, like that the sum is depending on an m, and I've seen that trick in anywhere before. So is that, and because we're truncating because it's only defined up to k equals m, but if I allow this thing k to be something greater than n, define that the Cm of m comma this thing greater than m to be 0, then I can change the k from the 0 to infinity, and this one is still same as before. So I think I'm extending that Faulhaber problem coefficient to be defined like this. If the second slot is even bigger index, why don't we call that one just 0, and then this whole thing can be written as a 0 to infinity. It's a neat trick so that you don't have to worry about when you're swapping the summation, you don't have to worry about this dependence. So now we entered like that, and I think I'm swapping again in here. So as you swap it again, then n to the k can go outside and bm must stay inside. So I nicely isolated 1 over n to the k thing, and here is everything else about m. So that's our coefficient that we're looking for. So here it is. That is the Sn without 1 over n, and I pulled out n in there, and this is 1 over k, 1 over n to the k, and this must be the coefficient that depends only on k here as m1 through like that. Now if you divide both sides by n, then Rn, the Riemann sum, now you have the full monomial term there, and with this coefficient. So now it's time to enter the formula of a CMK and BM, I think. Right? So I think I wrote it like this, and I didn't even mention about this radius of convergence and all that. So we can enter like this. You can truncate this to n, and I'm going to explain why this one converges, and later, and once it converges, and then we talk about the radius of a convergence and all that. And we can do all that just abusing this infinite notation, but what really happens is that you have to truncate it and dealing with a partial sum, and at the end, if it's high enough, and clear, something ugly happened at the tail, but you have this shape still, so all you have to justify is that this one converges, and radius of convergence of that creates for this entire power series is greater than 0, and then everything is justified. Alright, so using that convergence part, I'm entering this AK business there. So now that's our AK. So I'm emphasizing that we enter that shape, and we have to replace BM with the CMK. BM came from the Taylor coefficient of F. This came from Faulhaber coefficient. So Faulhaber's coefficient is beautifully described by Bernoulli using the Bernoulli numbers. So the secret to the CMK, which was the coefficient of this k to the m, k going from 1 through n. This is a polynomial of n to the first and coefficient there, and n to the second coefficient there, and all the way up to the n to the m plus 1, and there's a coefficient. That coefficient is now completely described like this using Bernoulli numbers. So now we're putting that one back in there. AK is the coefficient of that Taylor series of Rn. Bm times that CMK is replaced. Now what is Bm? It's a Taylor coefficient of F. Therefore it has this shape, mth derivative at 0 divided by m factorial. Now write it out, this binomial coefficient, m plus 1 factorial divided by product of these 2 factorial. Now you can see m factorial m plus 1, that cancels with m plus 1 factorial, and k factorial is there for Taylor series, and I'm going to put this m plus 1 minus k factorial underneath that one because I recognize that shape in there. So I put it on there, and k factorial goes outside. It's because the sum is about m. Now, like I said, I recognize this one. This is something you get out of differentiating the Taylor series multiple times. So let me formulate it like this. If you look at the usual Taylor coefficient with this monomial multiply, if you differentiate it k minus 1 time, you arrive right there as you keep canceling this factorial and what is coming down from that exponent. So if you do that, and you get this term. But if you want to look at it globally, the whole Taylor series, this index down here is not correct. This index must be k minus 1, so that we look at it as the derivative of f of x and plug in with x equals 1, so that disappears in here. So I had to change that to k minus 1. So that's what I'm doing in the next part, I guess. So I throw in k minus 1, but it's up to k, so I have to cancel out that k minus 1. What happened with the k minus 1? So if you go in and plug in k minus 1 there, that old 0, you're just left with the k minus 1 and 0 in there. Okay? But this is the Taylor series of the k minus 1st derivative of f of x. And plug in 1, then you get that value. So here I'm assuming that the radius of convergence of a Taylor series f of x includes 1, so that I'm plugging in 1 in there. So our result is limited to that part. So you have that, and I organize it, so realize that it's actually the k minus 1st derivative of 1 if the radius of convergence of f, the Taylor series of f, is big enough and containing 1. So this is neat formula. So solution to a Taylor series problem, AK is in that shape. T to the k, that's the 1 over k, 1 over n to the k, and AK was a Bernoulli number, plus this f part is formulated like this, k minus 1st derivative minus 0. Here, if you plug in k equals 0 there, and you end up in a negative 1 derivative, and it's usually not standard notation, but you can interpret that as the integral antiderivative, going backward derivative. So that coincides with our claim before the fundamental theorem of calculus. So that k equals 0, the very first term, picks up the antiderivative values at 1 and 0. So that is our one version of a solution, but I think there was a limitation. That is this if you look at it as a power series, the whole thing is the coefficient. What is the radius of convergence of this one? And when we enter that 1, we also had limitation. So I'm about to just go in and calculate this radius of convergence in here. Remember, the bk is even, so all the odd index in the Bernoulli numbers are 0. So when you compute the radius of convergence, you focus only on even index, and this is the kind of closed formula using the Riemann zeta function, closed formula of the Bernoulli number, and odd index is all 0. So if you take this adjacent ratio of even indexed coefficient, and from that we pick up all these terms. Okay, and this part looks really ugly. And what happens to that part? Riemann zeta function quotient is approaching 1, so it's mainly just 1 over 4 pi squared is what we have. It's reciprocal, that becomes radius of convergence, but we have no idea what can happen to that. I will explain that with an example, but let's summarize our limitation in here. First of all, we want this 1, because of that 1 we're using, we're assuming the Maclaurin series of f allows that 1 in there, and we're just hoping that this doesn't behave crazy so that they converge. So I'd like to introduce this as an in-depth version of a fundamental theorem of calculus. The very first term is the antiderivative value difference. That is the fundamental theorem of calculus, but it also gives you the next layer, and things like that. Great. So I chose cosine x so that these guys are bounded, right? This kth derivative, it doesn't do much. It doesn't make any complicated. So with that, it works. This whole thing is bounded, and this is the convergent series. So no problem. And again, going back in there, the radius of convergence of Bernoulli number pod is giving you 2 pi or something. So we have this version. So for cosine x, first term is the antiderivative value, antiderivative sine x, and the second term is the Bernoulli number 1/2 and cosine 1 minus 1. And that is f of 1 divided by f of 1 minus f of 0. And that's what this one is. So completely understood now what is making that second coefficient. So if you look at, I don't know if you have Sn in there, it doesn't have an Sn. But if you change that to Sn, let me write that down. Sn is sine of 1 times n, that is the linear part, and there's one constant involved in there, that's 1/2, second Bernoulli number, cosine of 1 minus 1. And rest of the part you can put in the little o of 1, and that's what's going on here. The second one is a little trouble example about that the radius of convergence. Also, the radius of convergence of this one itself is less than 1. We don't allow x equals 1 in the typical Taylor series of this one. We enter using the geometric series. So our formula of AK has a problem right there, 1. You can't use that in here. Also, if you actually compute the radius of convergence of this one, it's 0. With this, the ratio that I showed you earlier, it goes to infinity, therefore reciprocal becomes 0, so this radius convergence is not good. So basically our method does not work for this particular example, which was interesting in one example that I showed you earlier. But let's not give up. The right question is that I actually required very strong probability Taylor series, but our original question is that can we just use these numbers, still truncate in here, in that way there's no issue of convergence or anything. Is this still a good approximation formula? That is the right question to ask to save our work. Alright? Again, I have to think about the difference between the series of a function and asymptotic functions in there. There it is. The answer is yes. This formula we got in here is actually yes. And we can do the truncated version in our formula, but there's always a better way to do it. And our Mr. Euler did an integral analysis rather than that power series analysis. So it is it's much better. Always integral analysis is better. This is called Euler-Maclaurin formula. It's not about Riemann sum, it's just a general sum, but it can be used to Riemann sum. It's very straightforward corollary. So if you just add up 1 through, just like a Faulhaber problem, that what is this case when the hk is k to the m. In general, Euler has a wonderful formulation. As you can see, that is just, exactly the same formulation that I discovered using this analytic part. And he describes this remainder part nicely, and that's what we need. So let me introduce the remainder part. Remainder part uses an estimation of the Bernoulli number in there, and integral formulation because it uses integral bound and things like that. So that's the formulation. This doesn't behave too much, and this is the things that give us trouble. The key thing is that S is fixed. In the Taylor series, we have a remainder something like that. The problem is S is increasing. Here, S is fixed, all right, and n is going to infinity. But our problem is not really because it's really 0 to 1, so it reveals the answer. So how are we going to apply this formula, Euler's Maclaurin formula, to our situation? We have to change that hk into f of tn, right? So that's the k divided by n, things like that. Not sure if this is what I want. This t is not the same t, I'm sorry about that. This is just a dummy variable in here. But if you enter f of t over n in here, little composition, what is the derivative that is involved in here? As you use the chain rule over and over, 1 over n keeps popping out. So kth minus 1 derivative of ht is just k minus 1 derivative of this original function multiplied by power of 1 over n. Okay, so let me explain. I forgot about that. So if you replace that in there and then you pick up 1 over n to the k minus 1, that's the t part in there, and in here, and also we pick up the 1 over n. So as and also if you I think I have this all written out. Maybe not. I decided to not show it here. So I'm skipping that, but if you do the change of variable with this, replaced in there, it changed to 0 to 1. Okay? And then this is something approaching 0 as n approaches infinity. And we can turn that around nicely into this type of our asymptotic formula. Here I'm just using the 2s because it's even term, but you can just change to s and it is still true. Alright, so our Taylor series doesn't work, it's not a convergent series, but if you truncate it, it becomes a wonderful asymptotic formula. So that still survives. Excellent. So we can use our formula, not as a Taylor series, but an asymptotic formula, and our formulation still works. So I'm computing first few terms. The Bernoulli number, f1 minus f0, that's a part of our formulation. It turns out in this case 1 and 0 is negative 1/2. And you multiply these two, that makes the second coefficient there. So Rn is a pi over 4, the integral of this one between 0 and 1. And 1 over n times this coefficient right there, which is negative 1/4. And everything else is approaching 0 as n approaches infinity. So that's our first two terms of the Riemann sum when this one's the case. Okay, it's very nice. And let me remind you of our original problem. Ascend sum of all the values in between 0 and 1. Then you pick up this average value, and there is a negative 1/4 underneath it. So we saw that graph. I think I have in the next picture. This is Sn. We found that this asymptotic value, you subtract off, and what happened with that graph, we saw that it seems like it's approaching negative 0.25 by 1 sure, and it is actually true. It's not like log n hidden underneath it or something. So let me summarize it here. So what we have is a slightly deeper version of a fundamental theorem of calculus. Riemann sum approaches this number, antiderivative values of different values of antiderivative, but that's only the first term, and we have this wonderful depth of the change of the Riemann sum values. And for that, we summarize it as Sn, the sum of our values in between 0 and 1. We pick up this linear term, monomial term, with this coefficient definite integral, and the second term, before you hit the vanishing term, is 1/2 times the difference of the function value. And that was the answer. So I'd like to introduce this as slightly deeper version of the fundamental theorem of calculus. And if we had this old approach in a different way for the x to the m, e to the x, and sine x before. Right, for the rest of the part, and I'd like to kind of introduce a new notation to summarize this rather complex combination of coefficients of a Taylor series. So already I mentioned that the focus point is the whole thing is a given the function, continuous function, we'd like to come up with this formal power series, sort of. So here if I truncate an s and whatever the rest of the parts is error terms, so this is a formulation toward to the asymptotic formula, not the power series formula, because we know there are a bunch of examples that power series doesn't work, but the coefficient is still valid for asymptotic formula. So the focus point is starting from f of x and come up with this formal power series. If that's analytic functions, Taylor series converges, that's great, and that's starting from analytic function and end up in an analytic function. So I call that one sort of transform. It started from one function, end up at another kind of function. So I call that Euler-Maclaurin transform, motivated by the Riemann sum problem. So here I summarize it here, given f of t, and there's a formal power series. I'm going to call that g infinity t if you just extend that and look at it as a formal power series. And the meaning of that formal power series, or application of that formal power series, is this asymptotic formula. So emphasizing again, the series may not exist, but it is a formal power series. So using their formal power series notation, we can summarize our answer in this way to our asymptotic problem. Given the function, we construct this formal power series, and we already saw the answer to that each individual term. So the coefficient combination that we introduced earlier part is a bit complex, so I'm introducing simpler notation. Of course, is summarizing all that thing, but also notice there's something nice about that new notation, so which I call Euler-Maclaurin convolution. So you start with f of x and you end up at g of x, and how we're going to write that answer. Here is a notation that kind of shorten that all combination. So gx, let's say, is actually Taylor series or Maclaurin series, a power series, whatever you want. And hx in here, they're actually unconvergent series. And I'm going to define this convolution and g and h to be product of coefficient multiplied by k factorial. So because of the k factorial, we're kind of requiring that bk and ck, the growth rate, the radius of convergence, is pretty big, so that just like e to the x, so that you can win one of the bk and ck can have that k factorial in it, so that it is also convergent series. So we're only considering these things such that this is a convergent series. But again, we can look at it as a formal power series, and then there is no problem of defining things like this. So because the nature is defined as a multiplying coefficient, it behaves just like another multiplicative operation. With a 0, you end up at 0. It's a commutative because bk and ck, it doesn't matter how you multiply. And if distributive law holds, because bk is kind of distributed over, so these things are pretty easy to verify. And if it is a multiplicative operation, I might wonder what could be the identity operator. If you try e to the x, let me write that in here. The coefficient of e to the x is 1 divided by k factorial. That's for sure. So if you combine it with whatever, the ck becomes 1 divided by k factorial. And you can see k factorial cancelled, and it gives you bk again. So it's kind of easy to see why we have a gk back in there. There. And next one is at, let me also write it here, alpha to the x. If you throw an alpha to the x in there, and then you have alpha to the xk, x to the k, that's where this this part going in there. Hold on a second. I was correct. That's so we have alpha to the k coming out and x to the k there like that as you plug it in there. But it could have also come from throwing in alpha into the g of alpha, alpha x. Okay, you can't really distinguish that, e to the x there, and you will have alpha to the xk coming from a part of a bk. So these two things end up with the same thing. So I don't think I explained it very well, but you can try these two things and show these two things are the same. But because e to the x is identity, is a g of alpha x coming back there. So I noticed that this is one nice property about this convolution. And what I was surprised about this convolution that I defined, and I call the Euler-Maclaurin convolution, is the following. So here's a definition, and here's a surprise. If you differentiate g on star h, you end up at a g prime star and h prime. You don't see many operation that behaves like this nicely with a differential operator. So that was a bit surprised. That is something I want you to try. But when you're trying yourself, for example, when you're differentiating this one, g prime, you can see g prime looks like that. If that came from g, here's a k prime, here's a k coming down, and a bk, and x to the k minus 1. So that's what we have. But when you're entering these, so there's another one here, k factorial times k and ck, x to the k minus 1. That's g prime and an h prime. When you're doing this convolution, you have to multiply this k factorial stuff and with all these things multiply, but that coefficient is a coefficient of the k minus 1 power, so you have to multiply k minus 1 factorial and the product of all these things. And I was wrong about this. There's no k factorial. So I'm going to cross that out because it is only bk, k, and ck x to the k, so there's no k factorial. So if you multiply that, you have a k squared and bk and ck and x to the k minus 1. That's how it's going to have how it's going to work out. And there's a k minus 1 factorial, and if you differentiate this one, the product, you can see the k coming down and k minus 1, so that you can see k is here, and if you use 1k with that combined with this one, and there's a k factorial. So you can see that if you differentiate this one, you get that k factorial, bk, ck, and k coming down. So that's verifying. So I was surprised that it behaves really nicely, and it is even, it's also easy to see that if it works like that, the power series also works nicely with the integral operator as well. So there it is. So how are we going to use that to our asymptotic problems? So here we focus on this special function ex, and x times e to the x divided by a to the x minus 1. That's the Bernoulli number divided by k factorial and x to the k. You know our answer involves a combination of this one, so I guess we will be convoluting with this function with the other given function. So that's why we're starting with this one. So next one is that our f of x, if it looks like this, bk divided by k factorial, and our answer is a convolution of these two things, is f star and ex is bk k factorial, and the bk, that's the meaning of the convolution. Because k factorial multiply two copies. If you multiply k factorial, that's the definition of convolution, that cancels 1, so that leaves just this shape. So if you convolute two functions, that's what happens. And we want to use that for our formulation, which involves something like this. The k minus first derivative of 1 and k minus first derivative of 0 and things like that. So that's the part of the coefficient involved in there. So from f we have to pull that out, and I want to use this integral. So this k starts from 0. That's the how k ranges, varies. So the first one is interpreted, f negative 1 derivative is interpreted integral. So I started with this one, and I'm able to show how problems are formulated. So next part is that f of x is written like this. It's a Maclaurin series. Again, in this formulation we have to allow this radius of convergence is big enough, so include 1. So here is, I think, the Taylor series at x equals 1. So they plug in 1, and that's a Taylor series. And if you plug in x plus 1 in there, again allowing the wide range of radius of convergence, and then we switch to that form. So f of x plus 1 minus f of x. Then if you subtract these two, you get that coefficient we want, which is the part of our answer to our asymptotic problem. So we consider f of x plus 1 minus f of x, and we enter this type of power series, assuming that they behave nicely. So that's one formulation. So that part right here, convoluted with our capital EX, and that'll be our formulation of answer. Also, instead of using the capital F of x, I use this integral symbol, and that's exactly the same thing, and that there is this power series formulation if it has big coefficient, radius of convergence. Then EX is there. So if you think about convoluting these two things, like before, two copies of k factorial, but you will only pick up 1 because k factorial is multiplied, then multiplication of these two things. That's the convolution right there. So GX is defined like this, and that's exactly convolution of these two functions. So I'm writing as this integral from x to x plus 1, and with this special function EX that is coming from Euler-Maclaurin formula, or that thing that I discovered at the beginning. So that is the transformation. We start with f of x, you do this integral and convolution with that special function, and that's the one formulation of this, the answer we introduced before, using this new notation star. So if you apply that to e to the x, and here's what happens. E to the x, and if you stick it in there, then antiderivative is e to the x plus 1 minus e to the x in here, and because of the distributive line and all that, e to the x is common. That's the function part stays, and the constant part is pulled out. And e to the x is multiplicative identity for this convolution identity, so therefore it's just e to the x, and you end up at this transformation. Of course, it's e to the x that behaves nicely with e to the x that has e to the x in it. I mean ex that has e to the x in it. So x to the m, this is then we're going to discover the Bernoulli's identity again, but it is not really proof. It is just you know, using this notation, just recovering that information. So here, g to the x is according to our formulation of this particular definite integral times our ex. Then if you do the integral, m plus 1 and the difference of these two m plus first powers, if you subtract them off, x to the m plus 1, x to the m plus 1 cancel, and all the rest of the binomial coefficient survives and is convoluted with ex. Then what is this convolution? It's coefficient, two coefficient multiplied, and k factorial multiplied, so they cancel from k factorial is there, but there's no k factorial in here, but it's underneath there. But anyway, that's a correct formulation. So we have that coefficient. So that's the quote polynomials of a degree m, and that's associated with x to the m, and that's the complete answer to Faulhaber problem using Bernoulli coefficients, so that we are recovering that in this problem with x to the m. It is possible to apply that to the sine x, but it's not necessarily simpler than the one that we showed you earlier, so I'm not going to do that in here, but using complex variable functions, complex versions of sine x, and you can still play with this ex, and that's one of the reasons why we had that nice answer back then. Alright, I'm back to this problem that I introduced earlier that a lot simpler that everybody encounter these functions, and I addressed that before. So what is the Taylor series of ax? And here is the coefficients. And what is the asymptotic formula? If you have an asymptotic formula, that is sufficient enough to conclude about the radius of convergence, and that's what that is. So here is actually exact formula using the Bernoulli number. We are only using this even part, and already is picking up only the odd coefficient, so that's how it's related. So that's why it's picking up even here. The odd index of a Bernoulli number is 0. We don't need all this exact formula. All we need is an asymptotic, simpler formula. So I'm entering asymptotic versions of a Bernoulli number. There's a zeta part there, but it's approaching 1 as k is getting bigger and bigger. So this is really the simplest asymptotic formula there. Usually the version replaces factorial with Stirling's formula, but this is good enough for us. So now absolute value of this ak is now all these two things. Asymptotic version of these two things is simpler, so I'm replacing with the 16k and 2k factorial, and bk, if you divide that, they disappear because 2k is in the denominator. So we're just left with so here using this 2 pi raised to 2k is coming from the asymptotic formula of a Bernoulli number, so that we have a lot simpler version like this. If you replace that into this formula, and we have this asymptotic versions. So once you have this asymptotic formula of the coefficient of ak, then we can compute the radius of convergence. So ak plus divided by ak, and this behaved sufficient for multiplicative version, so you can easily verify that it's a 16 divided by this part in here squared, 4 pi squared. So 4 divided by pi squared, and it is the radius of convergence of this power series term, which is squared term for those coefficients. So you have to enter like this. So what is the square part? Pi squared divided by 2, therefore the radius of convergence indeed all the way to the pi over 2, where the vertical asymptote is. So that is the asymptotic formula of the coefficient of a tangent x, and from there we can compute the radius of convergence nicely. So here's pretty much a summary of my whole talk, which is advertised as a Riemann sum and fundamental theorem of calculus, but I'm doing backward. At the end, we saw that asymptotic formula of the coefficient of a tangent and a Maclaurin series of a tangent, and this is the asymptotic formula from there. So that's a nice asymptotic problem. It was introduced earlier, but we focused on this particular problem, the Riemann sum problem. Riemann sum is now analyzed further as an asymptotic formula like this. First value, constant value, is of course the value of a definite integral, and the second part in here is a further analysis in terms of the powers of 1 over n. But we also looked at this version Sn, which is the growing function. It's more fun. So the sum of all the function values, well-distributed x values, the function value at those well-distributed x values between 0 and 1, then we have this nice formula. Here is this main growth term. Next level of growth is this constant right here, 1/2 the Bernoulli number and the difference of function value. And rest of the part is something approaching 0. But we also have further analysis done on interval 1 as an asymptotic formula. But occasionally that can be extended as a Taylor series. So it's a series version, not asymptotic formula version. So thank you for listening. That is, well, I bump into this problem and got my own version of this solution, whether it's limited, but I think it is something for us to know, because many of the calculus textbook introduces this Sn version as meaning of these integral being the average value in between 0 and 1, things like that. So that's very nice information, and also very good introduction to the more advanced levels of a calculus for math majors or anybody who is interested in asymptotic formulas. So thanks.